Hi everyone, this is Sai Das, PMRF from the Department of Biotechnology, IIT Madras. And for your information, I'm recording this meeting. And today we will be learning the basics. Last class, we learned about the basics of calculus, an intuitive understanding of calculus. I hope the people who might hopefully be joining from now would have gone through the lecture video that I posted in my channel. You would have got access to that. And this week we would delve into, since you should be reading a lot about diffusion right now in the course, I would like to give you a simple three-dimensional understanding of diffusion. That is, you can think of all those differential equations in your mind, what's actually happening. You can visualize those. So that is very important. um, I would be giving you a foundational conceptual understanding of diffusion, so that when you look at all these partial differential equations and other differential equations that you might be you might be looking at over the course of your work, of your coursework, you would have an intuitive understanding of what exactly is happening in and what exactly you're reading, and just not mechanical. So that focus is also there. And I would now wait for some time, for perhaps 15 minutes or so, and after that I would start my lecture video. I'll start explaining the slides. So I hope people join in much before, like from last class. So the 15 minutes time is over. So I'm going to start my slides, start my presentation. So what is diffusion? You know, from the aroma from your mother's or anybody's food to the spread of dust across a room that causes allergies, and the blowing of the wind from one place to another, to a permeation of a ligand into of a drug or any other molecule for that matter, into a cell or its ligand. So ligand is a term that we use for the actually um, actually drug is interchangeably called into a ligand. This should be, a receptor. So so what is diffusion? If you just take a drop of ink and then just put it in a have you tried this, in a transparent glass bottle? I have not tried it, but have you visualized it? That's the question. And will you visualize it? Will you, after watching this video? Is that if you put a drop of ink in a transparent glass of water, what will happen? And why does it happen? Why doesn't the ink stay where it was and it spreads itself thin? So it no the thermodynamic explanation would be that the entropy increases of the system, whatever you can say, the universe, and the entropy of the whole system increases. But how do we measure diffusion? That is a question. So there are two things here. Um, the diffusion, when you add a drop of ink into a glass of water, what you create is called as a concentration gradient. And why there is a concentration gradient? Because there is, in some part of the system, um, a higher concentration of a different of a class of molecule, in this case ink, when compared to other parts of the system being the solvent. So to correct this anomaly, because of you know uh, thermodynamic favorability of the process, um, they call it an increase in the multiplicity of the process. People who would like to understand entropy, not just as an equation but as a measure of multiplicity, I would encourage them to read more on that. But for thermodynamic favorability, this concentration gradient has to be diffused. That is why diffusion occurs. Now, to what are the rules or the laws that govern this process of diffusion? So there are two laws. One is the Fick's first law, which states that the movement of particles, or the diffusional flux, the movement of particles per unit area per unit time, from high to low concentration, in this case the ink, from a high to low concentration, from the drop to the rest of the solution, is directly proportional to the particles concentration gradient. It's very simple. So basically, higher the concentration gradient, higher will be the diffusion. So we have an equation here, if you can see. It is J is directly proportional to d phi by dx, or J is equal to minus d into d phi by dx. So J is the diffusion flux, d is the diffusion coefficient or the diffusivity of the system. We will come to that later. Let us first understand what these terms mean, and then we will put these together to understand what the equation means. D phi is a change in the concentration of the particle. In our example, the ink. Change in the concentration profile of the ink. Once you put that ink, how its concentration profile at any given point changes. in the no any given point in the water changes. Dx is a change in position, which I just referred to above, referred to before. Um, so when you measure the concentration of the ink at different positions, position point in the system, which is the water, which is the glass filled with water, how the concentration, how the diffusional flux uh, moves is governed by Fick's first law. In other words, diffusion is diffusion is directly proportional to the concentration gradient of the particle. So if you see d phi is a change in the concentration of the particle, and dx is change in position. So d phi by dx is the concentration gradient of the particle. So uh, let's put this d phi by dx in the context of our example. So when I in the previous during the previous discussion, when I said that you just add a drop of ink and it starts to diffuse. So when you at time t equal to 0, which is the time when you add the drop of ink, all the ink stays in one place, and thereby a concentration gradient is created. Now like you say, you drop the ink at a position x1. Now at time t equal to 0, except for the point x1, all the other points inside the solvent system in the water, the concentration of ink is going to be 0. So but as the time increases, as the as we measure the let's take an arbitrary point x2 in the water system, nearer to mm, the place where you dropped the ink. And then what we do is, in fact, to say it okay, let's leave that for now. You take an arbitrary point nearer to the point x1, and then you keep measuring the concentration of ink. So how the concentration of ink at the point x2 changes with respect to the change in the concentration of the ink drop. That is what this is. So if you add a smaller ink drop, the diffusional flux is going to be lower, and if you add a bigger ink drop, the diffusional flux is going to be stronger. Now, before going to the second law, let's first look at this. So before I was referring to x1 and x2. Let us say that this is replace x1 and x2 by CA and CB, where CA is the point where you dropped the ink um, ink drop drop the ink drop, and CB is the point where you are measuring the ink drop at various intervals of time. Now as I said, if you increase CA, dCA by dx is going to increase, or in other words, if you increase the amount of ink that you are adding, the diffusional flux or the rate of movement of the ink particles per unit area per unit time, think of this area as the plane of the solvent from which the molecules diffuse from Ca to Cb. This is going to increase. So I'm repeating it again. If you increase the concentration of the ink drop here, the diffusional flux towards the point Cb will increase. This is what Fick's first law says. It's very simple. Now, if you take this equation and if you had followed my line of thought, you take this equation, and these slides will be available for you. You take this equation, you take case 1 of this of of slide number 5, if you see this, it's very simple, right? This equation, which may look it's intimidating just because of the fact that it is involving calculus, is just implying this: the rate of movement of uh, um, you know uh, a set of particles from one point to another point. That is a concentration gradient, because of a concentration gradient. That's all the fixed first law says. Now, so I picked up this slide from I picked up this slide from um, um, sciencefacts.net. It is very important in your scientific journey to attribute the source from where you pick for anything, for your presentations or for your publishing papers or whatnot. It's very important to give the source. Now let us go to the Fick's second law. Now it states the relationship between the change in the concentration gradient of the particles and time. What it says is, see, d phi by dt is equal to d into the second derivative of the rate of change of concentration with respect to position. Now, when you look at this complicated sounding equation, I would like you to think about velocity and acceleration. Velocity is the rate of change of a rate of change in position with respect to time. Acceleration is the rate of change of velocity, or in other words, acceleration is the rate of change of position in the particle. So it's the second derivative. So it is the rate of change. So see, all the other quantities are similar. The only thing that we are measuring here is the change in the concentration of to take our ink in water example. What we are saying is that, at a point CA, we are just measuring the change in the concentration of the ink, um, for that matter, at any point. You can, but you need to fix the point. So you fix the point in CA, and you keep measuring the rate of change of concentration of the ink from this point CA over a period of time. You will get a you will get experimentally, you will find out this: the rate of change of the concentration at a point with respect to time. So now, hello, is there somebody else who's there? Hello. Okay. So why is this the case? Why is this the rate of why is the rate of change in concentration? Hello. Hello, is there any other participant here? No. Okay. Why is it related like this? Now, so what I said is the rate of change of concentration at a point with respect to time is related to the rate of change of concentration at a given given point. So the rate of change of concentration with respect to time is related to the rate of change of concentration with respect to a given point. Now, what does this mean? So this looks complicated, right? This looks complicated to wrap your head around. Let me explain it to you graphically. Um, Let me explain it to you graphically. బాబా ఏదాచి ముఖ్యమైన విషయమా బాబా? Na perma pesta bye. So um, let me break down, in fact, this complicated looking equation and give you an intuitive understanding of it. So let's take two cases here. Okay, this is the point. This is the point of this is the point where the concentration of the ink is Ca, and this is the point where the now let's think of this as now let's keep the ink example out, because we have in the previous discussion I have used the ink example in a different context. Now let's say that let's take just two systems. Okay, some concentrate in a solvent system, in water or any other solvent. The concentration of a particle at a point A is Ca, and the concentration of a particle at point B is Cb. Now there will be diffusion because of Fick's first law. There will be a diffusional flux, correct? Now take this. Now let's say we have another bottle. We have the same particles. The concentration of the particle at a point A is Ca, and the concentration of the particle at a point B is Cb. Now what is the difference between this and this? It is the steepness of the concentration gradient, correct? That means here, let's take arbitrary values. If the concentration is 100 units, let's say the concentration here is 80 units. But here, if the concentration is 100 units, the concentration here is 20 units. So the concentration gradient is steep, correct? So for the same molecule, for the same particle, for the same system, if you apply a higher concentration gradient, you will have a higher diffusional flux. If you have a higher diffusional flux, the rate of change of concentration at a point A is going to um, you know uh, 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 it's going to increase. We can find out the rate of change of concentration of a of the system at a point with respect to time. So what it says is the rate of change of the concentration at a point A, or at any given point, um, is related to the concentration gradient that exists between two given points, and the steeper the concentration gradient, the higher will be the rate of change of concentration at a point A, where with respect to B, where the concentration at a point A is greater than that of the concentration at point B. So this is Fick's second law. So this is the foundation for everything, right? So this is the foundation for all, or whatever equations that you might have come across, in terms of steady state diffusion, unsteady state diffusion, etc. Pseudo steady state also will come. So but the foundation is this. So if you want to understand these equations, right, the mechanical looking at this equation, you just say you just mug this up. You can easily understand, take this equation and then put it, substitute it, use the assumptions of steady state or unsteady state, pseudo steady state, etc., and you can solve the question. You will get the answer mechanically. But if you want to understand it intuitively, you just need to look at this graph. That's all. It's very simple. So whenever you keep solving this equation, if you just if your creativity part of your brain, this will get lighted up, and you will feel good while understand that you have understood what you are actually solving. In other words, you would have not studied, but you would have learned something, which is a point here. Now I expected audience I would have asked what of in the first case, why is this sign negative? I would have asked this. And in the second case, in when after explaining this, what would be the impact on the diffusivity of the molecule? So just because the concentration gradient is steep, will the diffusivity of the molecule change? So diffusivity, diffusivity is just a proportionality constant here, right? So this J is directly proportional to d phi by dx, or equal to minus d into d phi by dx. This d is the diffusion coefficient. So if you do you think that just because the concentration gradient is steep here, will the diffusion coefficient of a molecule also change? If so, why? If not so, why? So that I would have, if there was an audience, I would have opened the floor. But now whoever uh, um, looks at this video, think about it. It's a simple question actually. Now let's understand what diffusivity is. The proportionality constant that seemingly typically we whenever we see this something is directly proportional to something else, we just say that then the next equation is going to be is equal to k into something. So this k would be mass transfer resistivity, mass transfer coefficient, resistivity, whatever, whatnot. But there is some interesting thoughts on this diffusion, this coefficient, or this proportionality coefficient. This proportionality coefficient, it's called diffusivity or diffusion coefficient. I typically call it diffusivity because lesser words. The unit is meter square per second. So here there are some particles. There are some particles here. There are some particles here. The number of particles here is greater than that of here. So it just moves, right? So it's just it moves with a velocity. Let's assume that it moves in a straight line. Let's leave out the complications of mean free path and molecules colliding and stuff. Like, let's assume that it moves, everybody moves straight. Okay, then it should be meters per second, right? Why it is meter square per second? I will tell you why it is meter square per second. Now when you when you when the even though a concentration gradient exists in a system, that doesn't mean that every molecule will just move straight towards the point where there's lower concentration gradient. They are not human beings like us, right? If you are hungry and there is food, we go straight running to it. But they are not humans yet. And so these molecules will just know what they will do. They don't have a mind of their own. Even though they see their lunch there, they will take first they will go straight, then they will come back, and then they will go at right angles to each to it. They will just move all around the place. This is how molecules behave, right? You would have learned about the theory of gases and stuff like that. Now let us take that assumption that everything moves in a straight line. It doesn't move in a straight line. The particles collide, and the particles can it can move forward, it can move back. Now let's assume a particle. Okay, it moves a certain distance delta x, and it collides with another molecule, and it comes back the same distance delta x. What do you think would be the uh, distance traveled by the particle? It's come back to its starting point, right? But it has done some work. So this is the difference between distance and displacement. So it went a distance delta x, and it came back a distance delta x. So the net distance traveled by this particle is 0. However, I however, what typically to avoid this inconvenience that there's a delta x and there is a minus delta x, what we do is we square the terms. So let's say that a molecule moves delta x, so the amount of distance it has moved is delta x square, and it comes to, let's say it collides and comes back minus delta x. What we do is we just say minus delta x square, so anything square is positive, right? So it becomes a delta x plus delta x is 2 delta x, so that particle moves is assumed to have moved to delta x. Now consider a system where there are typically even in micromolar solutions. In 1 molar solution there is an Avogadro number of particles. In semi-molar solutions there are lesser than that, but 10 power 23 and 10 power 16 doesn't make any big difference, right? There are huge number of molecules diffusing around, right? That means there are a lot of coin tosses. So somebody moves forward, somebody moves back, somebody moves this, somebody moves here, somebody moves there, and this is happening again and again and again in frames and frames and frames that we call time. And over a period of time, what happens is that we get a normal distribution. So what happens is that this is like flipping a coin, right? And if we keep flipping a coin, we will get heads or tails. The probability of getting the mean probability will be at zero point 0.5, and you will be seeing a normal distribution of probabilities, right? So this is how this graph will look like, normally distributed, which means that the mean distance traveled by a particle is 0. But that doesn't necessarily mean that all the particles travel only for 0. There is a decreasing gradient of particle who would have traveled as the distance increases. There's a decreasing number of particle who would have traveled that distance, and over a period of time, once after one standard deviation away or two standard deviations away, or even half a standard deviation away, we don't have any particles that are moving over and above that limit. So in effect, that is exactly why diffusion occurs. Just because the mean or the average distance traveled by all particle is 0, that doesn't mean that that is the only thing. It's the probability is normally distributed, and that is how diffusion, that is the driving force of diffusion, the probabilities. No, the driving force of diffusion is a gradient, but the mathematical approach to look at this, or a probabilistic approach to look at this, is to look at this as a normal distribution in terms of the diffusivity of the molecules in a concentration gradient. Even if there is no concentration gradient, let's say that the concentration is uniform, the molecules are still moving around, correct? There will be a normally distributed curve. Some molecules would have moved x distance more than some other molecule, compensated for by some other molecules would have moved lesser distance, and so on and so forth. Now I leave these things to yourself. What happens if the diffusivity is higher? The order of diffusivity in biological systems, what could it be? I would like you to figure it out. What you do is, a clue is that much of biology happens, in fact all of biology known to mankind till now happens in a solvent system, and that solvent is water, correct? So go look at the diffusivity of water, and then come to a conclusion what it should be or could be. Now finally, let's let's understand something called as active or passive diffusion. Now coming to the concentration gradient. Now let's say this is a cell, okay? The cell, this is a nutrient that wants to get into the cell. Assume a lipid bilayer here. I'm taking this example because um, this is a biology course, correct? So there's a cell here, there's a nutrient here which wants to come in, and there's a concentration gradient here. Now if you leave it over a period of time, this nutrient here will go here, go here, go here, go here, and by the time it comes inside the cell will die. Some essential nutrients. So in order to maintain an effective flux of uh, certain nutrients, cells have designed some systems which will facilitate this when there is a concentration gradient, it will facilitate uh, the entry of these particles into the cell. How it does, why it does, what are they are called receptors, and I will go no more, and I will leave the interested reader to read more about diffusion facilitating receptors, transporters. They are called ABC transporters. It's a very important impediment in cancer resistance. And but coming to this active versus passive diffusion, so this is the difference between active and passive diffusion. If you give this cell a time of 100 years, this concentration gradient will disappear. Ca and will be equal to Cb, but the cell does not have 100 years. It has to double, it has to meet its metabolic requirements, so it puts it some of its it has certain mechanisms which I just told you about to facilitate the diffusion. It is called as active diffusion, and without facilitation, when the diffusion happens, it is called as passive diffusion. Now, what is the difference between this active and passive diffusion? So this is as I said initially, um, this concentration gradient is dissipated because of thermodynamic considerations. Thermodynamically favorable for this process to occur. I told you that in the initial discussion. Now, just because it is thermodynamically possible doesn't mean that everything is hunky dory. It is thermodynamically possible, but I cannot say to the cell that wait, this is thermodynamically possible. If you give this the time, this will come in another 10 years. We cannot do that, right? The cell will die. So in addition to looking at the thermodynamics of a process, we need to also look at the kinetics of the process. So what the cell does here is it takes a thermodynamically favorable process and adds some receptors, which I said adds some mechanisms in its cell, which makes it kinetically also kinetically more or kinetically favorable, I would say, which is an increased flux of of the nutrient A into the cell. So the kinetics of the process is governed by rate laws. You should be aware of this by now. I'm not going to go into that. But thermodynamics versus kinetics, it is a very important distinction that you should know about if you want to pursue advanced biology, because everything inside the cell, from protein uh, from enzymatic conversion of a substrate to a product. I'm just giving one example. There are thousands of examples in biological processes. um, all these depend upon these differences, these subtle differences. So I don't want to go into that. I leave the if I have piqued the interest of anyone who has seen this video, I will leave it to them to explore and investigate this further. So this is about diffusivity. Now you would be, once you finish your once you see the videos and finish it off, you will be um, asked to finish other, complete assignments, both graded and ungraded. I would like you to give you a sense of how to go about it. First of all, read the question fully. Just after reading one data point, don't start calculating, read the question fully, understand what they are asking for, and sometimes they will ask for the flux, they will then sometimes they will ask about the concentration, then they will ask about the concentration gradient, etc., etc. Understand what they are asking for. That is very important. And in some cases they won't give you the diffusivity number. They would give you the system, and they would expect you to think about what kind of diffusivity this system could be, this biological system could have. So for that you need to answer this question: the order of diffusivity in biological systems. Those are the two things, and every other thing, all the equations, all the study material have been explained beautifully by the lectures given by Dr. G.K. Suresh Kumar, and you can just go ahead and have the listen to his lectures, read his book. But all the time, whenever you are solving a problem, you are not solving equations. You are not a computer that is designed to mechanically solve this equation. When you are solving a problem, it has something to do with this. So when you're solving a problem, after seeing this video, when you solve a problem, these concentration gradients, these different concentration gradients, etc., etc., flashes in your mind. That means that you have learned something from this video. So that's about that. I don't expect any more people to join here, so I will just wait till the time ends, and I will leave it at that. Thank you. It's beautiful, right? The aroma of your food to the blowing of the wind. To interested readers or to interested listeners, I would, I would ask you to think about something. Wind power and solar power are the same. Is this statement true or false? I mean, doesn't have to do anything with the biological implications of diffusion, but wind power that powers the turbines that ultimately generate the electricity, and solar power where you can see all those solar panels and etc etc etc. Wind power sector and the solar power industry both are big industry right now, and we need the support of those two industries, but essentially they are both solar energies, or in some way we can say that essentially it is a it is energy derived from the sun. Why? How? I mean, for solar energy, it's very simple. Sun's rays strikes the solar panels, and you get electricity, photoelectric effect. But for wind systems, how can it be considered solar energy? You think about it. I'm the people who figure out the answer would. It's a nice journey, perhaps. I would leave you to that. So, just a minute more left to go. Understand how wind is created. Why there are winds blowing from one direction to another. Why is there a concentration gradient of wind at two different points in space in our Earth? If you understand that, you will easily answer the question. Alright then, it's time. I wish you all well, and I hope you are making progress in your understanding of biological systems. Thank you very much. Bye bye.